I'm Felix, and I'm going to be talking to you about systematicity and generalization in a situated agent. It's actually been debate for quite a few decades about whether or not neural networks are good at generalizing beyond their experience. So Jay, one of our authors, produced a book with many examples of good generalization in neural nets. At the same time, Stephen Pinker said that the generalization was not like how humans generalize. Jeff Ellman produced a compelling demonstration of language learning in a recurrent network which can make predictions beyond its experience. But Gary Marcus pointed out that its ability to do so was lacking that of adult humans. One thing that connects the work in all of these studies is that the data from which the networks learned to perform these generalizations looked something a little bit like this, whereas, as we know now, if we didn't before, the real world, in fact, looks something a little bit more like this. In our work, we took a sort of compromise position and used the Unity game engine to create a room with scattered objects and a large bed and storage tray in every episode. In it, we placed a neural network-based agent which could take one of 18 discrete actions in order to interact with the world. The agent had a convolutional network for processing the vision and a recurrent network for integrating experience over time in order to choose the right actions. To train this agent, we instructed it to lift all of the different objects that it could encounter in the environment and gave it a reward when it lifted the correct one. We also trained it in a putting task where it had to put a specified object either on the bed or the tray, which occur in every episode. But importantly, we didn't train it to put all of the objects on the bed or the tray. We held out a subset of the objects that it had been trained to lift to test whether zero shot it could integrate that knowledge with the knowledge of how to put certain things on a bed or a tray in order to execute novel combinations instructions in a zero shot way. Interestingly, we found that the agent was just naturally able to do this. So here you can see that it performs at about 90% on the test set, and in the video you'll see it's a little bit uncertain, but essentially with these held out objects, it's able to put them in the right place without ever having been trained to do so. And that seems really quite systematic, which seemed to go against some of the predictions in the literature, but we wanted to understand this phenomenon better, and in particular have a sense of when it might fail or when we can rely on it. To do this, we created a grid world, which was a little bit like the Unity 3D room. There's the single white object, which is the location where the agent has to take a given object in a good episode. It's kind of the analog for the bed. And then to compare it, we created a 3D scenario that was as close as possible to the grid world. And importantly, when training and testing these agents, the set of underlying instructions is exactly the same in both conditions. What we found was that the agent trained in 3D was able to generalize much better than the agent trained in 2D. Exploring a little bit further, we were able to isolate this effect, a large proportion of this effect, down to the egocentric perspective that the agent in 3D has. To show this, we gave the agent in the 2D grid world an egocentric perspective in the form of a window which followed it around the 2D environment as it moved and restricted its field of view. When we did that, we actually found that its ability to generalize to the novel instructions increased to almost the level of the agent trained in 3D. This tells us that the egocentric nature of reality can provide useful invariants for learners that can in turn promote not just generalization, but also systematicity. In another experiment, we explored the effect of acting over time in an embodied environment. In one condition, we gave an agent color shape instructions and a particular training test held out task, and the agent was able to move up to objects and bump into them. In another condition, we just gave the agent the first frame of every episode. So it's not so much an agent as a visual question answering model, which has to just say left or right when given a particular instruction. We performed the same sort of holdout task as in the previous section, and we found that the agent that was able to act and move through the environment over time, getting many more views of the same objects, was actually able to generalize to novel instructions more effectively than the agent which was just trained like a visual question answering system. This tells us that active perception of our surroundings can yield data that usefully augments the agent's experience, and that in itself can promote not just generalization but also systematicity. Just to conclude, we know that neural networks are arbitrary function approximators and that they can either be quite systematic or disappointingly unsystematic. But our work suggests that their ability to generalize in ways that we want can increase as their experience of the world becomes richer and more realistic. One thing that's worth remembering then is that the conclusions we arrive at, if the world that we train our models in looks a little bit like this, may not be the same conclusions that we arrive at if the world looks a bit more like this. I'll leave you with a clip of our agent having fun in the room. Thanks for your interest and come and see our poster.